All right, let's jump right into this explainer and build a bridge between intuitive, everyday problem solving and the strict, logical instructions that computers actually require. If you've ever wondered how we take a messy human problem and translate it into flawless computer code, well, you are definitely in the right place. We're going to break down the exact foundational concepts you need to master algorithmic design. So here's our roadmap for today. We're taking a progressive formalization approach. We'll start with everyday problem solving, compare algorithmic versus heuristic solutions, look at translating problems for computers, organizing the solution, flowcharts and pseudocode, and finally wrap up with some key takeaways and rules. Let's kick things off with something highly relatable in Section 1, everyday problem solving. Okay, so these are the 6 fundamental steps of problem solving. I highly recommend you just go ahead and memorize the sequence for your exams and assignments, because skipping even one of these steps will completely derail your whole process. Step 1 is simply identifying the problem, but step 2, understanding it, that's where a lot of people trip up. You actually have to define the knowledge base. If you're writing instructions for a human, you can assume some basic background knowledge. But if you're solving a problem for a computer, that knowledge base is strictly limited to the programming language you're using. From there, you identify alternative solutions, pick the best one, list out your step-by-step instructions, and finally evaluate to see if your solution actually worked. To put that into perspective, look at this example of the 5th step using the incredibly everyday problem of just going to work. We've taken an intuitive morning routine and formalized it into a highly organized sequential list. Notice just how explicit it is. Wake up, brush your teeth, take a bath, dress up, have breakfast, leave home. A computer can't just go to work. It literally needs every single one of these actions spelled out in exact sequential order. And that brings us perfectly to Section 2, Algorithmic versus Heuristic Solutions. You'll definitely want to note this down. It's a classic exam concept. There's a huge difference between algorithmic and heuristic solutions. Algorithmic solutions are totally straightforward. They can be reached through a direct series of actions. Think baking a cake or balancing a checkbook. Computers are absolutely phenomenal at executing these. But heuristic solutions, those are messy. They require reasoning, built-up knowledge, experience, and a whole lot of trial and error. Think about deciding which stock to buy or figuring out how to speak a new language. Historically, computers really struggle with heuristic solutions, unless they're powered by artificial intelligence, which actually allows them to build a knowledge bank and interpret context. So how do we actually make a machine understand us? Let's dive into Section 3, Translating Problems for Computers. To build that bridge to a machine, it's kind of like a translation pipeline. First, you take the raw problem, and you use your human logic to develop a step-by-step algorithm. Then, finally, you code that algorithm into a program. The program is what the computer actually runs. It takes an input, processes it, and spits out an output or result. Listen up closely here, especially for your assignments. A computer will execute your instructions in the exact order you give them, but it relies entirely on you following strict syntax rules. Syntax is basically just the grammar of the computer world. It's the rigid set of rules governing whatever specific programming language you happen to be using. If you miss a comma or misspell a command, the computer is totally lost. It simply cannot understand you. And when you break those syntax rules, you get a bug. A bug is just an error in a program, and hunting them down is a process we call debugging. But keep this major pitfall in mind. You might write code with absolutely perfect syntax, meaning the computer flawlessly understands what you typed. But if your logic is flawed and the instructions are out of order, you've got a logic error. And guess what? The computer will blindly execute those out-of-order steps and cheerfully hand you the completely wrong answer. To stop those disastrous logic errors before they even happen, we have to carefully organize our solutions. So, Section 4, Organizing the Solution. Let's look at a standard payroll problem as a quick case study. Our very first tool here is the Problem Analysis Chart, or PAC. This neat little 4-quadrant box is where you untangle a messy real-world problem. You separate the given data, like the hours worked and the pay rate, from the required results, which would be the gross pay. Then, down in the bottom left, you explicitly state the processing required. In this specific case, the equation is gross pay equals hours multiplied by pay rate. Finally, you list any solution alternatives. This chart essentially guarantees you know exactly what you're starting with and exactly what you need to deliver. Next up, we take that pack and we build an interactivity chart. This gives us a really nice top-down structural view of our program. Notice how the main big task, payroll control, is broken down into smaller modular subtasks: read, calc, and print. This modular approach is just incredibly important in programming. It lets you tackle one specific action at a time, which makes the overall solution so much easier to write and test. And here is where it all comes together, the IPO chart. IPO stands for Input, Processing, and Output, and it acts as the ultimate bridge. It takes the data from your problem analysis chart and the modules from your interactivity chart and just merges them. It explicitly traces how the input data, hours worked, and pay rate flows through a numbered sequence of processing steps, and it maps each step to a specific module, ultimately resulting in the output of gross pay. Honestly, if you can fill out an IPO chart correctly, you've essentially already solved the logic of the entire program. Once our data flow is fully charted out, we move to Section 5, Flowcharts and Pseudocode. You are absolutely gonna need to know these standard flowchart symbols for your exams. Flowcharts use specific shapes to strictly dictate actions. Flattened ellipses, those are for the start and end of a module. Rectangles are exclusively used for processing blocks, like mathematical calculations. Parallelograms indicate input to and output from the computer's memory. And diamonds represent decisions, where the flow literally splits based on a true or false condition. Knowing these universal symbols means any programmer, anywhere in the world, can read your logical plan. Check out how these three distinct ways can represent a problem before it ever becomes actual code. Take a look at the calculation module. You can write the algorithm out in plain English steps, or you can draw it as a flowchart, visually showing the entry into the module, the processing rectangle where gross pay equals hours times pay rate, and the exit. Or you could write it as pseudocode, which is essentially just code-like statements that represent the logic, but without you having to stress over the strict syntax of a specific programming language. This right here visualizes the ultimate truth of programming. The system rigorously follows flow lines from beginning to end, executing one single step at a time. The arrows guide the data from the start, straight down through the read block, into the calculation block, down to the print block, and finally right out to the exit. It perfectly reinforces exactly why initial logical planning is mandatory. If an arrow is pointed the wrong way, the computer is going to follow it anyway, resulting in those fatal logic errors we talked about earlier. All right, let's wrap this whole thing up with Section 6. Key checkaways and rules. So, here's a quick recap for your notes. Always identify the problem and clearly define your required knowledge base first. Remember that computers absolutely excel at algorithmic problems, but those demand clear, step-by-step instructions. Watch out for logic errors. They happen when you have perfect syntax, but your steps are totally out of sequence. To avoid that nightmare, meticulously plan your flow using problem analysis, interactivity, and IPO charts. And finally, when visualizing your logic, always stick to the universal flowchart symbol rules. I want to leave you with something to really chew on to test your new problem-solving skills. If you see 3 numbers on a page, almost anyone can instantly point to the largest one. It's totally intuitive for us. But how would you map out the exact logical steps to teach a computer to do it? How would you structure the decisions, the comparisons, the inputs, and the outputs? Thinking through that, breaking the intuitive down into the incredibly explicit, well, that is the true art of computational thinking. Thanks so much for joining me on this explainer, and happy problem solving.